Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it's an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Alright guys, step on inside, and although I haven't done any videos with you regarding logarithms, at least not in the last like 5 or so years, not since I've been on camera, let me show you what logarithms are all about, at least in the small context that we're in right now. Going into next week or so, you'll get another bit of review on logarithmic properties and other things that are a little more explored with them. But this is a start with them, how to convert them from exponential form, how to evaluate some of them that we're able to do in a non-calculator form, some things on natural logs, and then how to graph them. Those things are going to be covered here. So let's get straight into it, guys. I got a little review for you right here. Let's start with, actually before these, in terms of doing these, convert them from exponential form to logarithmic form and vice versa. Let's make sure we understand what that conversion actually looks like. If you have, this is considered exponential form here, where you have something with a base raised to a power and it equals some result. If I have some base b raised to some power y and my result is x, the conversion to this, see logarithms, when you do a logarithm for something, your result is the exponent. So you're going to get something to equal y here by doing a log. You take log with base b of this value of this x. This says b to this power becomes x. You know, that's what this is here. And, just us understanding, writing that conversion out is going to be all too important for when we actually evaluate logs in the future. A little more so being given a log, being able to write it in this form so you know exactly what's being asked. So let's just jump straight into it right now. And yes, we are going to be writing log each time, or in some cases, natural log. Now, we're not solving anything here. Everything that's going to be stated is just a true statement. 2 to the 7th power is 128. That's just fact. Now, there's a logarithmic version of this, log base 2 of 128 equals 7. If you had a calculator that could apply base 2, which ours will default to base 10, some of them can't change base. There's a way to trick it. I'm not going to talk about that today. There's a way to trick it to call base 2. But if you can use a calculator and type log base 2 of 128, the result's going to be 7. That's what the answer is. The result of a logarithmic evaluation is the exponent. That's what we're doing. That's what this conversion is. We're just practicing and understanding what it actually means when we write it. I know some people are going to be confused what goes where and such. Hear out loud what I'm saying. 1/3 to the negative 4th power is 81. Log base 1/3 of 81 equals negative 4. The result is the exponent. 1/3 is the base. Yeah, the 81 is that last little bit you have to put in there. So there's that. Now this isn't log times anything. We're not multiplying log with something. Log is a function, a logarithmic function, just like a square root, just like f of x and whatever, just like sine and cosine. It's a function for something, and that's what we're doing. We're taking the logarithm of 128 given base 2. And it answers that exact question. Now over here, this one's a little bit different because there are no actual numbers here, but we can still write it out. Log base p of the square root of r equals q. And there are a lot of logarithmic properties we can talk about in the future when it comes to square roots inside of there. I'm like seething at the teeth to try and start writing them out. But right now it's just converting to those forms right there. And that's great. Now, this will be a little more practical for you going the other direction. If you're given log base 6 of 1296 and you're asked to evaluate it, to find out the answers for, how do you do it? Well, now we know that the answer's 4 here, and we're going to talk about them when we do these. But, you know, we convert it to their exponential form. We say 6 to that power, whether it's unknown or whatever, is 1296, right? You would be asking yourself 6 to what power is 1296? And this is us writing it in exponential form now. We're going to be doing that for these other ones. Now this one's interesting because you do not see the actual base on this one. So one thing I'm going to write out for you up here is the log of x, there's an implied value here, and it's not actually 1, it's 10. Log base 10 of x. I think I mentioned in your calculator, it does base 10. Unless you have a way of tricking it or changing it. You assume it's base 10. So it's log base 10. So that means this is a 10 that's right here. Whether you want to write it or not, it's up to you. But you got to write it for this next part. This is 10 to the 6th power equals 1 million. And that's, again, just writing a true statement for ourselves. Now this ln means natural log. And natural log is log base e. log base e of x, like that. Now, you're not going to see them write this. You're going to see them write natural log. It's a very common thing to see right next to log, like log of 10. Log base 10, I should say. So natural log is log base e. So this, another way of writing that is log base e of 1 equals 0. Now, one thing, I'm going to mention this a little later. It's going to be important for graphs, but log of 1 is 0 regardless of base, because anything, especially including e, to the 0 power is 1. Any non-zero number to the 0 power is 1, and so that would end up being that result. So those are those conversions there. I wouldn't call them answers. These are just conversions to these things here. And then we are going to be evaluating some things right now. So here is where you are going to be given logs, and we are actually going to evaluate what they are. Remember, this will equal some result. We don't know what it is. For the sake of practice, I'm just going to write an x for all these equals x, because I'm going to go ahead and convert them for you. I'll write their conversion version of them, so it kind of helps us understand what it is we're trying to find. Remember, the result's the exponent. When I evaluate log base 2 of 64, I'm asking myself 2 to what power is 64? And this is something I'm kind of asking people to do without a calculator in this sense as well. I know you have to work a little bit to get that, but 2 times 2 is 4. That's 2 squared. 2 cubed is 8. 2 to the 4th is 16. 2 to the 5th is 32. 2 to the 6th is 64. This is x equals 6. In other words, log base 2 of 64 is 6. If you could type it in the calculator, that's what you'd get. It is 6. Okay, log of 1 over 1,000 equals x. Remember, the implication is that's a 10 right there. So this is 10 to the x equals 1 over 1,000. And the question is what exponent goes here. Now, before I answer it, I do want to go back to this number 2. I don't know if you recognize that the negative exponent right here. If you remember, negative exponents don't mean negative numbers. They mean some form of division. You divide by 1/3 4 times from 1, and you get 81. Dividing by 1/3 is multiplying by 3. You flip this thing here. How does this 10 turn into a fraction? And you might know the answer off the top of your head here. What I'm going to do is work some change of base principles to show you how it helps for future problems. But again, you might know the answer. But here, what I'm going to do instead is say, let's try and turn this into base 10. Let's match bases. And if we match bases, then the exponents will be equal. What I mean by that, just as a simple property here, is if you have two of the same base, if a to the b power equals a to the c power, well then b equals c, right? The exponents equal each other if they have matching bases. So let's match these bases. Let's turn, we know that 1,000 is 10 cubed. Okay, is that same base yet? Not quite. We need this to be 10 to some power, not 1 over 10 to some power. Well, 10 cubed is 10 to the negative third power. So you can see where I match bases to figure out that that exponent is supposed to be a negative 3, right? And yeah, maybe this is something you could have just done on your own, totally fine. You might be colorblind by the black here. I'm going to go and change colors. But yeah, that's kind of one way to work it out. And like I said, it's going to be more helpful for some other problems to definitely consider doing that. Like, let's take this one, for example. Log base, where's that green? Log base 9 of 3 equals x. That means 9 to the x power equals 3. Well, again, this can come in one of two different forms here. It's kind of your call. Let me show you a way that if you didn't know how to work this out, like if you didn't know what this exponent is, what I really would do. If you can't change the 3 to a 9 in some sort of way forming exponents, you're like, 9 to what power gives me 3? Obviously, that's what we're trying to work on. Turn the 9 into a 3. Turn this into 3 squared. 3 squared to the x power is 3, right? 9 is 3 squared. Now, why does this help you? Because these exponents end up multiplying. That's a property that we've used before. 3 to the 2x power equals 3. Now, this 3 is 3 to the first power. So what I've done was I've given myself a version of writing this in such a way. In fact, I might use this in the future in terms of talking about this. As far as talking about why these exponents work the way they do. Now they've matched bases here, I can set these equal to each other and solve that equation. If 2x equals 1, divide both sides by 2, x is 1/2. Yeah, 9, in other words, 9 to the 1/2 power is 3. I mean, this is something that my class knows about very much so, and if you followed my videos, you probably know that the fractional exponent ends up giving you a square root, in this case, to the 1/2 power. But this is a nice other cool way of looking at this, and I think I got to do it for number 12. I think I got to do it for this problem later as well, and just talking about, this is one of those change of base things that actually really proves beneficial to you and something that you know how to do, working out another property. And then, therefore you get something that kind of matches. And I just set that equation equal to solve for x there. So that value is 1/2, or 0.5, as a calculator might give it to you. Okay, let's see what's going on down here. 2/3 to the x power. Now you gotta use parentheses here. 2/3 to the x power equals 8/27. So we gotta figure out what that single x is that raises 2. If this helps you, raises 2 to some power and 3 to that same power to give you an 8 and a 27. Know what I mean? 2 to what power is 8? Does 3 to that same power give you 27? If so, then the statement works the way we wanted it to. Yeah, 2 cubed is 8, 3 cubed is 27. This x we're looking for is 3. That's the answer there. Natural log of e to the 6th equals x. If it does help you to have that little rewrite, and I probably won't do this much in the future, log base e of e to the 6th equals x. Natural log is log base e. This one's interesting. A lot of people have trouble with this, and there are other ways we're going to do this in the future anyway. This asks e to what power gives you e to the 6th power? Well, 6. Now, this is one you can do in your calculator straight up. Same with the 10, actually. Or the number 8 here. Log of 1 of 1,000, you can get -3. Because there's no change of base thing, there's a natural log button in your calculator, and you're going to get 6. So it's, I don't have to know what e to the 6th is to work it out. I have to know what I raise e to get e to the 6th, if that makes sense. And that's what we get there. All right, number 12 is a very special one. As far as what to do here, I have 4, if you know the conversion now, 4 to the x is 1/32. There is no way that you can raise 4 to an integer power to get 32, much less 1/32. It looks like we have to deal with negative exponents, but it looks like there's more than that. What I've kind of mentioned in some of these other problems when you looked at number 8 and number 9 was this change of base thing really helped. If you can get the bases to match, that would be nice. So the question is, although you can't raise 4 to an integer power to get 32, can you raise some base to some power to get to both 4 and 32? And the answer is yes, it's 2. Now there are other ways to do ones where you can't change base with things, but then you do need a calculator if you want to get something that doesn't just say log with it. But here we're going to get an exact value for us, and let's check it out. 4 could be written as 2 squared, So we do 2 squared to the x power. And the parentheses are all too important as far as stressing the order of operations and what we get to do with these exponents together and things like that. Now, you saw how we worked these things before. 2 to the 5th is 32. So 2 to the -5th, let me do this in order. 2 to the 5th is 32. So 2 to the -5th is 1/32. Well, I get to multiply these exponents here. So this becomes 2 to the 2x power. So I actually got to match bases here. If I can get a base of 2 in both of these, it allows me to now set the exponents equal to each other. Now I solve for x here. If 2 to the 2x equals 2 to the -5, well, then 2x equals -5, and x equals -5 halves. -2.5. -5 halves, that ends up getting you your answer. Trickier. Definitely trickier, but it's just among those things that it's still solvable without a calculator completely. All right, here we go. Solve for the variable in each logarithmic equation. So this is just, this might be a little different from these. Now you're not solving for the exponent, you're solving for the missing base or the missing value. Log base b of 125 is 3. That means that b cubed is 125. Whoops. And if you want to solve this, you would take the cube root of both sides. And you would end up getting b as 5. So that base that would go there is 5. That's all. So we're not actually solving logarithmically, but we're using our conversion principle to make sense of the equation we set up in order to solve it. Now this one, keep in mind, this would be a log base 10 right here. So 10 to the -4th power is x. So x is, 1/10 to the 4th power, or 1/10,000. I don't know, 0.0001, I think, if you write it that way. And lastly, b to the -1st power is 0.25. So what does the b value have to be here? This one, there are a lot of different ways that you can write out this form. Because are you going to take the -1st root of both sides? Is that something you want to be a fan of? I don't know. Let's say you didn't have a calculator. You know what that thing meant. To the -1st power, we know that means 1/b. And if you wanted the fraction equivalent of this, 0.25, I sure hope you know, is 1 over 4. Well, same kind of things as before, guys. If 1 over b is 1 over 4, well, b is 4. Multiply both sides by b, multiply both sides by 4. You get the picture. B is 4 there. 4 to the negative first power is 0.25. Yeah. So that's some of the work there. That's how we're going to do it. All right, and the last side right here, or the second side, as we do these graphs. Now, I don't know how long I can stick around talking about the graphs in full. These are things that my students already got to work on a little bit, and I'm going to play to them more than a larger crowd for now. Apologies to that. What I will state, I'll get into it a little bit. I state that I won't, and it probably will. The problem is you have to see everything at once. I got to build with them on what does it mean when you just change base, then what does it mean if you do horizontal and vertical translations, then what does it mean with the stretch factor, then what does it mean if it's natural log, if it's negative. You have to see it all at once. So I'll get into it, but it's all at once. And these are the ones that are kind of hard to use a table for. You could, but then you'll either deal with a lot of decimals or you're going to be picking and choosing a lot of numbers till you find your integers, unless you understand what logs mean, or you understand the inverse of the exponential function. And that's what logarithm graphs are. If logarithms give you exponents, then they are the inverse of exponential functions. And the general form for this thing is f of x equals a times log base b of x minus h plus k. Now, in order for this to work best, you are going to have to have known something I've done with graphs in the past. A represents your vertical stretch factor. H is your horizontal translation. K is your vertical translation. Now, I'll deal with these in some certain ways that'll help you a little bit. B is your growth factor, if you will. It's your base value, but try and think of it as your horizontal growth factor rather than your vertical growth factor from your asymptote, like we did in exponential functions. Again, you're going to have work with me in the past a little bit to totally make sense of this. Otherwise, this is just an answer key for you, or I talk a lot. So here we go. What I want to start with is the horizontal translation thing. Now, the first thing I want to mention with logs is they are indeed inverses of exponential functions. Exponential functions have horizontal asymptotes. Logarithmic functions have vertical asymptotes. That's because you have a domain restriction. If you understand the idea, I got to write some other stuff out. Log of 1, log base b of 1 is 0. So it doesn't matter what your base is, log of 1 is 0. I want to make sure you know that. This is going to be very important. And in your log stuff, your domain is x is greater than h. The idea, and it's not always going to be written that way. You have to make sure that I'm going to be looking inside the thing. Actually, let me say this. X minus h has to be greater than 0. The inside thing, the thing you take the log of has to be greater than 0. You can't take the log of anything and get 0 or get negative because there's nothing you can raise a positive number to get you 0 or negative. It can get really small positive or really large positive or anything in between, but it can't become 0 or negative. So the first thing I'm going to talk about is the horizontal translation because I want to talk about the vertical asymptote. Your vertical asymptote occurs at x equals h because that is where you're restricted on your domain. When you look at number 16, f of x equals 5 times log base 4 of x plus 2 minus 3, the domain here is that this x plus 2 has to be greater than 0. The thing you plug in for x needs to be such so that when you take the log of that inside value, it's still a positive number. That's the only way that you can get actual numbers out from it. So subtract 2 from both sides, x has to be greater than negative 2. This is where all your points will exist. That means your vertical asymptote is at x equals negative 2. Your vertical asymptote is at x equals negative 2. It's a vertical line that goes like this, and all of our points will be graphed to the right of this. And when we talk about end behavior, here's the domain. Right here, state the domain. When we talk about end behavior, we'll make sure to know what the heck that's going to look like. The first point I'm going to find on my graph is always going to be a consistent 1 unit away from the vertical asymptote because it's the x value that I think someone homered over here, because it's the x value that we get to plug in so that we're taking the log of 1. See, when I plug negative 1 in for x, this isn't how I'm going to say it. I'm generally going to say 1 to the right, 1 to the left, whatever. When I plug in negative 1 for x in this equation, negative 1 plus 2 is 1. Log base 4 of 1 is 0, right? 5 times 0 is 0. So what happens when you plug in a value that's just 1 away from the asymptote in the direction of your domain? This part turns into 0, period. It just does. It doesn't matter what kind of log graph it is. It doesn't matter if it's natural log, doesn't matter if it's negative log, doesn't matter. that will turn into 0. Then you're just left with this k value. And that's where you get your vertical translation, this minus 3. When I'm 1 away from my graph here, I'm going to have a point that is 3 down, at least in this problem. So there's that vertical shift. If this wasn't here, I would be at 0. If this was a plus 3, I'd be up here. If it was, So that part just kind of goes to show that that's that vertical translation, and that's always one consistent point we're always going to get. Everything I do after here will have to do with the 4 and the 5. Now let me pretend like the 5 wasn't there just for a brief moment with you guys. The 4 is, remember you raise 4 to some powers to get whatever number goes inside here. 4 to some power. So these numbers need to be powers of 4. 1 is a power of 4. 1 is 4 to the 0 power. 4 is a power of 4. That's 4 to the first power. What are other powers of 4? Do 4 squared, you get 16. 4 cubed, you get 64. 4 to the negative first power, you get 1/4. Remember, the result of the log is the exponent, but the thing inside of here, the thing we plug in for x, or x plus 2, I should say, the thing that goes in, is the result of that exponent. 4 to the 0 is 1. 4 to the first, 1 up from here. 4 to the first, remember the result of the exponent is the y, is 4. I'm going to go 4 away from the asymptote here. It's 4 times further than my previous value. 4 squared, if I go 2 up, would be 16. Now don't plot these points yet, by the way, because this is a 5 right here, which we're going to change in a sec. 4 squared, if I go another power of 4, I'm going to be 16 away. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 away like that. Another up 1 on y, another up on the exponent is another 4. I know I'm speaking really fast on this here, but the idea, if you know my exponential functions, is every time we increase x by 1, we multiply by another 4 from the asymptote. Now every time we increase y by 1, we're going to multiply another 4 to the right on the asymptote there. Another 1 up would be 64 away, and then 256 away. You keep multiplying by 4. Now, as I decrease my output by 1, then my input I would have to be 1/4 that amount. You divide by 4, so it's about 1/4 there. So that's what would be happening here, and I would connect the dots for the graph. The difference is there's a 5 here. And the 5, remember, the 3 is already accounted for. We already subtracted 3. We're already 3 down. The 5 is going to be a vertical stretch factor. Everything will be shifted 5 times more separated vertically than they were before in relation to your original point. Right here, the negative 3. So what I mean by that is instead of just going up 1 right here to go 4 over, I'm going to go up 1, 2, 3, 4, 5 as I go over that mountain. From here, I'm going to go up another 5. 1, 2, 3, 4, 5. Because you're not going up 1 each time now. You're going 5 times more than that. Down 1, 2, 3, 4, 5. Like that right there. So this is what this graph looks like instead. Everything is 5 times taller than it was before. Again, 5 times taller. This is going to be pretty hard for me to graph. Don't speak too soon. That was actually pretty nice. And it approaches the asymptote there. Remember here, it never truly flattens out. It starts to flatten out a little more, but remember, there's something else that's 5 times higher up when you hit 64. Way over here, right? It's another 5 up from there. And you keep going. End behavior. End behavior states as x goes as far as it can in one direction, in the other direction, what are you approaching? So my end behavior here is as x approaches positive infinity, your y approaches positive infinity. You know, your range is all real numbers. This goes forever up and forever down. There's no y value you can't hit. You can plug in some x value and you'll always get any y value, and any y values possible. As you can tell, you'd have to plug in very numbers that are very close to -2, like -1.9999999, you know, like that, and you're going to get very low y values as a result that goes toward negative infinity. And that's what we say here as x approaches -2, but it only approaches -2 from one side, from the right side. So what we do is we put a little plus there. This means kind of -2's right hand limit. As we approach -2 from the right side, y is approaching negative infinity. We're going down forever. So that's the end behavior of this right here. Normally we say as x approaches negative infinity. The difference is we have a restricted domain and we can't state exactly that. Okay, I know I went slowly on that one, but you can see where I'm going to be compelled to speed up a little bit more based on what you just heard there. Let's see how much more we can enforce. Number 17, f of x equals negative log base 3 of x plus 6. Let's start again with that domain, the idea that the inside thing you take the log of, not just x, but in this case x is all that's inside, has to be greater than 0. That's your domain, straight up. Domain x is greater than 0. That means your vertical asymptote is at x equals 0. It's right on the y-axis. So we start, whoops, wrong color, hold on. We start right there, and every point will be to the right of it. Now, the next point I'm going to find is 1 to the right of it, because when I go, and this is perfect, because this is plugging in the value for x that I'm also taking the log of. When I go 1 to the right, it's also log of 1. You know what log base 3 of 1 is? It's 0. 3 to the 0 power is 1, so it's 0. You know what negative 0 is? It's still 0. But you know what that plus 6 is? It's 6. When I'm 1 away from here, I am 6 up. This is my starting reference point. Everything I do will be in relation to here. Now, this negative means negative 1, right? If this was a positive 1, it would say every time I increase my y value by 1, I'm another factor of 6. I'm another power of 6 further out from my asymptote. But because it's negative, you flip it over. You reflect it over this bit right here. Instead of going up 1, I'll go down 1. Where I then, sorry, I said 6, I meant 3. I go down 1, I'm going to multiply by 3. Boom. 3 times further out from my asymptote there. Now you can try this. Let's try this together, because these are actual x values. I don't have to do major plugins here. Plug in 3 for x, that's 3 away from the asymptote. Log base 3 of 3 is 1, because 3 to the first power is 3. Remember, the result's an exponent. So it's 1. You do negative 1 plus 6. That's 5. Okay, there's that point. If I go down another one, I'm going to be 3 times farther away at 9. Let's check that one and see if that works. Log base 3 of 9 is 2. Negative 2 plus 6 is 4. So see, it's kind of, I mean, it is inverted. I mean, we did these with square roots in the past as well. You would try to find out the number you got to take the square root of, but sometimes it's easier to just say what that number is squared to figure it out, right? We know that 4 and 9 and such are perfect squares, but sometimes it's just easier to kind of talk about it that way, especially with logs. Now, I can't fit 27, which would be the next bit over, but that's kind of the point I was saying. You don't want to plug in 10 and 11 and 12 and 13. You'd be plugging in 16 more numbers, 17 more numbers before you find 27. As the next integer. Yeah, you'll find the points in between, but that's what the curve is for. Now, right here, if I go up 1, right, that's when we're dividing by 3. So we'll get a 1/3, 1/3 of the way from the asymptote right there. So these are the points I can fit. This is what I'm just going to go ahead and use right there. 1/9 is kind of a little too close for comfort, and I'm going to draw the curve anyway. So let's draw that one. Now, the thing about the curve on the other side I'm going to be picky about is that you don't cross y equals 3 at this time. I got to make sure this graph doesn't do this, because otherwise I would have found these points, right? And I don't completely flatten out either. It's kind of that in between. You got to just keep working itself. And there's your graph. Now the end behavior says as x approaches infinity this time, y approaches negative infinity. We're going down as we go further right. Now as x approaches 0, because that's the from the right side, right? As we get closer and closer to 0, y is going up forever. It's skyrocketing upward. And there's the end behavior on that. Okay, number 18. Hopefully it's making sense, because I'm saying all of these in one fell swoop. I'm giving you everything in one bit, A, B, H, and K. And that was the point that I said that I'll have to go a little bit fast, because my students have heard it, and they got to progress through it. You didn't. I'm sorry. The A is 1/2, the B is 2, the H is -4, and if you didn't know that, we're going to go ahead and start off just by talking about domain. I think it's important. You got to find domain anyway. Just go ahead and say the thing you take the log of has to be greater than 0, so x is greater than -4. The k value is 0, though, right? The plus 0. That means there's no vertical translation. There's a horizontal one, right? The vertical asymptote is at x equals -4. So we are going to start right here. I'm going to start right here. Yep. Right there. And our first point we're going to find will be 1 away. That's at -3. That's when you take the log of 1 and get 0. Times 1/2 is 0. Plus nothing is 0. We start right here. There is no vertical translation. When we're 1 away, No vertical translation. Everything I do based off this will be double my distance away every time I go up half the amount that I normally would. Normally I'd go up 1 to double it, 1 to double it, another 1 to double it. Now we're just going to go up half that amount, which is halfway, which is half, 1/2. You go up 1/2, you double that, you get 2 away. You go up another half, you double that, you get 4 away. Go up another half, you double it, you get 8 away. Go up another half, you double it, you get 16 away. That's probably all I can fit there. Next one is 32 away. You go down a half, you take half of 1, and that's a half. Go down a half, take half of a half, it's a quarter. And again, all I can fit. Maybe, hopefully, it's making a little more sense now with how the stretch factor works with all those. You just do it like this. It's easier to do on a piece of paper because I can rotate the paper. I can kind of rough sketch it. And I end up drawing right what I'm looking at. Here I'm drawing on a tablet instead of on my screen. Because if I could finesse it, if my finger was on the screen right there and I could actually draw, that'd be better. All right, there's the graph. So here's my domain. Now I want my end behavior. As x approaches positive infinity, so does y. I'm not saying y or f of x. I've just been saying y. Y approaches positive infinity. You could do either or. And as x approaches what? -4, the right side of -4, y approaches negative infinity. Okay, last one, a graph, and then we write 2 equations of graphs down here. Number 19, f of x equals natural log of 1 minus x plus 3. All right, some things get a little more confusing here. First of all, it's base e, which, just to help you out, e is around, because I'm not going to use a calculator, it's around 2.7. There's a little more approximation than that, but that's as much as we could even try and graph. When you square e, when you square e, it's around, believe it or not, it's around 7.2. Kind of just reverse those. And if I divide by e, it's around 0.36. It's about a third. Which is kind of nice. 3.6 is kind of not half of 7.2, but it's 20 times less. You can kind of think of half of 72 and think about those numbers without, it's kind of nice. Okay, so anyway, the really confusing part about this, and you can kind of tell by the graph in and of itself how it's kind of left facing. It's not because we shifted so far to the left. Well, it's for other reasons. See, domain. Don't get too hell-bent in thinking just take the opposite of this number and that's your asymptote and all that. No, there's a little more to it. Domain says 1 minus x has to be greater than 0. The things you plug in for x, you have to make sure that you keep your values positive. So what's going to do that? If I subtract 1 from both sides and then divide both sides by -1, you get x is less than 1. See, the inequality flips when you multiply or divide both sides of an inequality by a negative. The symbol flips. Your domain x is less than 1 means we're going to be graphing points to the left, not to the right. See, if I chose points that were more than 1, if I chose 5, you'd be doing 1 minus 5. You can't take the log of -4. Not natural log. That doesn't work. But if I tried to plug in -5 into here, you know what 1 minus -5 is? It's 1 plus 5, 6. That's a positive number. So, when you plug in values, not just negative, you can plug in 0. 1 minus 0 still works. But, when you plug in values to the left, that's when you are taking the log of positive values. So it's really negative x values that rule the world here, not the positive ones. So anyway, but your vertical asymptote here is still at x equals 1. And it's a positive 1. See, it's not a negative 1. You don't just flip that sign. Be very careful. You're not just flipping the sign. You ask yourself instead, what value do I plug in for x to give me 0? That's what's always been the case for all of these. I know people are so used to flipping the sign, but that's a result of what kinds of equations we had in the past. Now it's a little different. In fact, we did these with square root graphs in the past. So now instead of going right 1, because that's not in our domain, we go left 1. See, if I plug in 0, and I already mentioned this, when you plug in 0, 1 minus 0 is 1. That's when you take the natural log of 1, which, hey, is 0, right? And then the plus 3. So when I go over 1, that's when I get 0. Plus 3 is my vertical translation. All right, every time I go up 1, because there's no vertical stretch here, every time I go up 1, I'm going to be e times farther out, or 2.7 times about farther out here. So up 1 is e times farther out to the left, so 2.7-ish. Up another one is another e times farther out. It's about 7.2-ish. So 3, 4, 5, 6, 7.2. Okay, like that. Another e times farther out would be around 20. And 20 can't fit. I didn't provide you it. It's close, though. It's probably somewhere about, like, right there. So it's pretty close. But I'll kind of leave it. Now, 1 over e is close to 1/3. So I'd say ish like that. And, yeah, that's it. You get any closer, you're just literally going to get closer. So I'll leave this as the kind of end there where we're curving out logarithmically. And there you have it. It would be interesting in the future when we start doing more with our log properties in terms of solving what the actual x-intercept is, setting this thing equal to 0 to solve for it. I mean, that's something we theoretically could do a little bit of. I don't think anyone's ready for it yet, but it's possible. Oh, yeah, we could. Yeah, check this out. If we set this equal to 0. Sorry, I'm trying to think what it is we do and don't know. You could subtract 3 from both sides. I'll just write it this way. 1 minus x equals -3. That means e to the -3rd power is 1 minus x. Add x to both sides, subtract that. You get x is 1 minus e to the -3rd power. So if you want to know what that... Do I have my calculator with me? Hold on 1 second. Here it is. 1 minus... I know no one cares about this. E to the -3rd. 0.95. So it's really, right, it's really close to 1 right there. Listen, I could have divided a couple times by e and figured that out, right? But that's, you can also figure that out kind of in that way. Really cool. All right, so anyway, that's the x-intercept. Let's go and erase that. End behavior. Good thing I'm color-coded because I'm going to fit this right here. End behavior. As x approaches, here's where I'm going to say, let's go to the right. We're going to get as close to 1 as possible, but from the negative side. Not the negative side, to the left of positive 1. Y approaches negative infinity. And then as x approaches negative infinity, y approaches positive infinity. As we go forever left, we go forever up. Okay, two more. Number 20, we have to come up with the equations now this time, right? So it's going to be that form, f of x equals a times log base b of x minus h plus k. So all that involved, let's kind of do what we did before if we had our own graph. We established what the asymptote is, what the domain was, all that kind of stuff to get us the graph that we need. The vertical asymptote, you can kind of tell, is this guy right here. This is what we're approaching. The point I always found after that was when we were 1 away from the asymptote, which is right here. And this helped establish what your k value was. Right now I can tell, it looks like my h value is 1. My k value is 2. H is 1 because we're shifted to the right. Now, in our equation, it's going to say x minus 1. Right? That's that whole idea. It's x is greater than 1, therefore x minus 1 is greater than 0. Therefore, this is the thing that goes inside the log, right? It's x minus 1. But that's the idea right there. Now try and find some other points right here that look like you're hitting, those integer values like this to kind of establish what's happening next, right? This is when we are 1 away. This is when we are 3 away. This is when we are, looks like 9 away. So it looks like your b value is 3, Looks like the b value is 3. We're tripling right here. Not every time we go up 1, looks like the a value kind of has its own place as well, right? Every time we go up 4. This is up another 1, 2, 3, 4. Up another 1, 2, 3, 4. There's a vertical stretch in a value of 4 right there that allows us to come up with the equation. Y equals 4 times log base 3 of x minus 1 plus 2. Cool, huh? Now, I'm not going to require domain and end behavior, but I could. All right. Last one. Actually, am I? What are the instructions? State domain and end behavior. Yeah, I guess we should. So domain was x is greater than 1. And end behavior says as x approaches positive infinity, so does y. My infinities are getting pretty bad looking. And then as x approaches 1 to the right, y approaches negative infinity. All right. It actually helps to use the domain for this next one anyway, because we're going to the left. So last one, number 21. Your domain, you can tell here the vertical asymptote is on the y-axis. So your domain is x is less than 0. Now, what this means, in order to keep the thing inside greater than 0, if I multiplied or divided both sides by -1 right now, this would then say negative x is greater than 0. What this means is to keep your log things positive, you're going to have to take the log of negative x. It gets a little tricky. That part gets a little tricky there. The h is 0, but the thing inside, because of the domain right here, I mean, this is the domain, but in rewriting the domain, it helps you understand what we're taking the log of. When the x turns negative is when you graph left. That's what changes it, right? That's what changes the inequality. So there's that part of that. The k value comes next as far as like, okay, when I go 1 to the left, I'm shifted down 1. So the h is 0, okay, but we go to the left, remember that. The k is -1. And then we find some other points that we end up hitting here. Looks like we're just going up 1 to find our next integer value as we seem to double. This is 1 away, then 2 away, then 4 away, then 8 away, then apparently 16 away. We're doubling each time here. The a is a default 1 as we go up, but the b is 2. So we have the information. Keep in mind, as we go to the left, that's a negative x there. This will be f of x equals, it's just a 1, so log base 2 of negative x, and then what was this, -1? -1, like that. And that ends up being that graph. So there's your domain. I'll go ahead and drag that down. Oh, I want to bring down everything. That's okay. There's your domain. And your end behavior is as x approaches 0, but to the left side of it, y approaches, looks like negative infinity. And as x approaches negative infinity, y approaches positive infinity. There it is. Okay, that is all of it. So that ought to do it for this one, guys. I want to thank you so much for watching this one, trying to clean it up, get another look at all the answers here. That ought to do it for this one, guys. This is Mr. Robinson. Thank you so much for watching. You know, coming in the future here, like I said, we'll do more with logarithms, exploring their properties. If you start to understand that logarithms are just inverses of exponential functions, and you know your exponential properties, I'm not saying it should be a breeze, but it should make some sense, especially when you do more and more. That'll do it, guys. Thank you so much for watching. Take care. I will see you in that very next one.